Can anyone confirm that I have can anyone confirm that you are receiving my voice? Yep. Yep. Okay. Thank you so much. All right. So we're back to our course. So a few announcements. The problem sheet is supposed to be online, but I don't know why it's not online. But it's ready to, when the problems are there. I think one of the instructors will take care of that for this week. We'll try to keep it regular each week, maybe each Friday, but sometimes we need to add some other problems, so we don't do it. But this week there is a nice problem there, which will allow you to solve the value of a series using double integrals and change of variables. And this series is very important in mathematics. So I'll try to do that exercise. Okay. All right, so we are a bit behind schedule. We'll try to catch up this week. So the plan for today is to finish this line integral. And then we'll talk about the fundamental theorem of line integrals, and then start Green's theorem. So these are cool things because they have a lot of application in physics actually. And actually all of these concepts, they are actually from physics. They were introduced by physicists and then it became part of math for the higher dimensional structures. But in the beginning, it was a purely physical concepts. So people, they were really talking about those mass and center of mass. And the line integral is, as you will see, is actually the work done, as I was explaining the last time, is actually the work done by a force. So this is actually the line integral. The reason why these line integrals that were introduced is because it gives you the right quantity that you can transform. For example, when you compute the work, it gives you the exact quantity you have to consider if you want to transform an energy from one kind to another one. For example, if I am pushing an object against the wall, and that work that I will do, it will be transformed into heat energy, right? Because of the friction. So, and the heat energy will be transformed into, well, the heat energy, right? So the right thing to take is actually those line integrals. So when you compute the line integrals, when you push against an object, so what the value of the line integral, it'll give you a number. If you take that number and you take the wall, for example, and you start analyzing that wall, and you convert that amount of energy into how much heat you will get. This will depend on the properties of the wall, and you must have seen that in chemistry, right? If you have a certain amount of calories and you have a solution of salt with water, and it has the kind of a number associated with it, which tells you how much degrees it will gain if you give that solution a certain amount of energy. So that number, the line integral, is exactly the quantity that you want to take. If you want to transform, uh, if you want to go from motion energy, which is a kinetic energy, to heat energy. So that will allow you to move from one kind of energy to another one. So this is exactly the origin of those line integrals. All right, so the last time I stopped an example, there was actually a mistake. Thanks, so someone was reading my note. By the way, my notes are online, and there was a mistake on my notes. So not, but we didn't do that example. He was just reading it ahead of time. So evaluate the line. Okay, and what is C? Oh, admit. So what is C? C is actually but only this part. So this is the curve C. And a curve has always a direction, an orientation. Okay, so this is the circle x squared plus y squared is equal to 16. Okay, so the thing with these line integrals, you just have to remember the formulas and uh, just apply them, right? So you always have to give a parameterization of the curve. So a parametric, so we choose a parameterization of C. So for a circle, it's always cos and sine, and it's a radius 4, right? So it's 4 cos t, 4 sine t, and t is always between. Now it's from minus. I mean, you have the choice here. It really depends on you. You can go from 3 pi over 2 to, but you have to go past 2 pi. But if you start from minus pi over 2, then you have to land on pi over 2. But you really have the choice to choose whatever you want. Whatever orientation. I mean, if you start by 0 here, then you have to do this. Okay. Okay. And now remember, what is the ds? So this is xt, right? Remember, this is xt. and this is yt. So r prime. So ds is square root of, remember the formula I gave you the last week. ds was x prime t squared plus y prime t squared dt. In this case, it'll be 16 cos square plus 16 sine square of t dt, which will be 4 dt, right? Hence,
Oh, wait, I'm sorry. Is that square t square or is it x prime?
oh, okay. I see what you mean. So it's x prime, the whole thing squared. So it is square root of x prime t squared plus y prime t squared. So that's the formula. You have to remember it. Minus, no, it's minus here. Minus pi over 2 and pi over 2. Okay? And now you integrate this. So the line integral over c of this function ds is equal. Now ds is this thing, right? Is now ds is here. But here is the thing. X and y is a function, but you need to, it's a function, but that lives on this line. It's a function that is defined everywhere, yes, but we are integrating over the line C, over the curve C. So X and Y, they should be evaluated at the curve, on the curve C, right? So you should evaluate X, Y along the curve C. So at the point of the curve, which is parameterized by the parameter T, right? What is X? For a certain T, what is X? X is 4 cos T, and what is Y? It depends on T, it's 4 sine T, right? So at each T, we have this. And now we integrate over the all, over the curve. What is the curve? It goes from minus pi over 2 to pi over 2. Now, once you have done this, that's it. It's just first year calculus. So it's 4 to the power 3 sine square of t over 2. And by the way, if at some point in the problem set or you're stuck doing an integral, the point of this course is not to make you learn how to make these integrals. So they're not supposed to be hard. If not, then try to do it by yourself. But it's not supposed to be hard. It's either change a variable, that will tell you or give you a hint how to do it. How did you derive ds? Yeah, yeah. So this is this. I did it here. So this is ds. Right? And then I plugged it into here. Does it answer your question? Now you know where it was. Yeah, okay. Okay, so remember, what is this integral? We took a line, we took a curve, and basically, what is exactly this number? I mean, it's 0 here. But what is this number? Is you take a function of two variables, and at each point, at each little tiny part of the curve, we took this ds, we multiplied by the value of the function, and we did this for all of these, right? And we did it. That's, you know, and then we took the limit, and then it gave us the integral. So of course, it's going to give 0, even though this ds is never 0, because you're just basically, it's a length. The whole integral can be 0 because the function itself can vary. It can be 0, it can be -1, -2. So the whole thing can just play out in a certain way such that by the end, it's going to give you 0. So here's the thing. We can define also other line integrals. We can define other types of line integrals. So the first one is, what is this? The first one is you integrate a function, you take a curve, take a function of two variables, and now instead of ds, you're gonna take dx. I'm gonna tell you in a moment what does it mean, this dx here, right? And then we can also define another type of integral, which is fx y dy, okay? So keep these two equations here. I'm just gonna draw a diagram so that you can understand what I'm saying. So again, I'm just gonna recall what we were doing. We took curve, right? We took a curve, and then we took the line t, which is the time, right? And then we divided this line into, for example, if we started at A and then you landed at B, we divided this into very small subintervals. And then we call this Ti minus 1 and this Ti, right? And for each subinterval, we had a sub arc of the curve, which was associated with this subinterval. And then we call this thing dx, right? And then we took a random point that belongs to this ds here. Inside this ds, we call it a sample point, right? And then now we can do the exact same thing, because when you move from ti minus 1 to ti, remember, this curve is a parameterization, right? The curve is given by xt and yt. This is the curve. So when you move from ti minus 1 to ti, you actually move not necessarily the same amount, but depends on the function, but you will have a delta x here. It goes from xe minus 1 to xi. And the same thing happens in the y-axis. You move from yi minus 1 to yi, right? And this is the point here. Uh, well, it's supposed to match with, it's supposed to match with, I'm sorry, this is not a really nice diagram, but it's supposed to match with, and then you have, supposed to be a vertical line, all right? So we can do the exact same thing with delta x. This is delta xi, depends on I, and this is delta y. It's very different from what we were doing with double integrals, because in the case of double integrals, our freedom was, we had the freedom to vary x and y. Those are the variables. Now the variables are not x and y. The variable is only one variable, it's t. This is what you can vary. And that's why here it's a constant width in this subinterval. Here is not necessarily a constant one. So we can do the exact same thing here, which means that we take a random point inside, we take a random point inside the interval, right? Here is the limit, and then we take the sum, and then we'll take the limit when n goes to infinity from 1 to n. Now we take a point f x I star y I star, right? A point here and a point here, and then we multiply by delta x I, right? And this is some point here. And then we do the same thing. Okay. Now we would like to evaluate this. Uh, we would like to evaluate these sums. All right. Because delta xi is actually approximately equal to, not approximately, sorry. Now delta xi is equal to x prime ti star delta t, right? This is the mean value theorem. Okay, this is the mean value theorem. For some t and ti star inside the interval, we get, could you scroll? Yeah. So we get that this integral fxy, please don't hesitate if you have any question, because we did the same thing last time. So I'm supposing that you remember, but of course of course you cannot remember uh, unless you really review these things. Um, so the integral here is actually, that's exactly the same as we did the last time. So you just plug this into here, right? Plug delta xi in here, delta xi here, right? This thing, you put it in here. So it'll give you x prime, t star, xi, y star, and you know, then you will have a Riemann sum. Okay, you will have a Riemann sum. Yeah, and we will not go through the details because again, this xi star, y star can be chosen to be exactly the same as the image of this ti. I mean, this will give you exactly a Riemann sum because the ti star, when you put it in here, this is a sample point. You can choose whatever you want. So you can choose the one associated with this ti star here, and it'll, since this ti star is in here, xi star, yi star will be inside also. So, and same thing for ti star. Here is a little bit confusing because here uh, I'm saying xi star star, yi star star. Maybe it's better if I just do this. But I'm just gonna keep it here because I mean you can be confused of this x star star and this x star 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 here, but it's actually, you can just take xi star to be the image of this parameter here. But let's focus just on x star on delta x, right? So let me go a bit slowly here. So it's the limit when n goes to infinity of the sum when n goes to n to n of f uh, f x I star star I star star x prime t I star delta t. Okay, but as I was saying, this xi star is just something that is inside here. Right? So you just can take the xi of t star, right? And it'll give you a Riemann sum, right? Right, which is a Riemann sum. So this line integral is actually the integral which is one variable function times x prime t dt, and now dt goes from a to b, right? Similarly, the integral Okay, I hope this is not too fast. Okay. Uh, right. So if I, so here, if I give you, so given a function, so instead of fx right now, given a function p, xy, given functions pxy and qxy. So we have seen what does it mean to compute this integral here, right? Let me just do dy, right? And this is a number, and we have seen how to compute this thing here, right? You just apply the formula. So this is in general will be denoted by this. Compute, this is what you will see actually. Compute this. So they give you two functions and they tell you compute what is it that I'm doing? Yeah, so sorry. I just don't want to. So this is dx and this is dy. Let me just, a lot of typos on my notes. Just be careful. Dx, dy. Okay, so this is by definition. Okay, so remember this. Remember this. Okay, so when they tell you compute this, is actually compute these two things. Example. Okay, so let's do an example actually. So this is, yeah, compute where C is the curve Now let me do something else. on C1 on C equals C1, C equals C2, and C equals C2. And here we have orientations, which we will take them to be this, hopefully. Oops. What did they say? And then C3. No, I'm not sure. C2. Did we? Yeah. Okay, so first, so remember, these are not smooth. This is, I mean, these are not smooth. This is not a smooth, because one of the things we were careful with is we wanted the curve to be smooth, which means that the derivative exists everywhere. But here are the tips of these triangles. The triangle, um, it's not a smooth curve. This is not a smooth curve, but it is piecewise. Piecewise smooth. Okay. All right. So actually, let me see. No, sorry. That's another example. C is actually C1 union C3, C2, and C3. Okay, that's a closed curve. I don't know. I think I have the same example, but for vector fields, but we have to compute it on each one. But we will have to compute on each one, but I'm just making sure that. Or is it just C1, C2? Ah, okay. No, sorry. Okay. I got it. Okay. Sorry about that. This example is this. Okay. That's a very good example, actually. The example is compute this on C1 and C2, right? And C to be C3, right? So we would like to do, yeah, we would like to compute the integral on C1 and C2, and then do the same thing for C3, and just observe that although it's the same endpoints, so we start from the origin, 0, 0, and we end on this point here. I'm just going to tell you in a moment what is this lines. But we would like to understand that it depends on the path that you take. That's going to introduce us to conservative vector field. So I'm not, so in general, you have to find a parameterization, but here's the parameterization. So this remains true. This is not a smooth curve. C1 and C2 is not a smooth curve, but it is piecewise smooth. So the integral on C of x plus 2y dx plus x squared dy is equal to the integral of C1 but the whole thing, right? It's not, be careful. It's not the first one on C1 and the second one on C2. It's the whole thing. It's you have to compute. It's this on a curve, okay, or along a curve. Okay, so a parametric equation of C1 is given by xt is t and yt is 1 over 2. Okay, and t between 0 and 2. And then the same thing of C2 is, yeah, I'm just gonna let you write down this. Is xt is equal to t, yt is equal to 3 minus 2. And t is between 2 and 3. So this is 3 and this is 1. So so x prime is equal to 1 and dy dt is equal to 1 over 2 on C1, okay? And x prime is equal to 1 and y prime is equal to minus 1 on C2, okay? So here, I'm gonna go slowly, but make sure you understand. So the integral of the whole thing we wanted, x plus 2y dx plus x squared dy, right? So I'm using these two here. I'm using these two equations here. Okay, so I'm gonna do it in one shot, but make sure you understand it. It's the curves. I'm on the curve C1, okay? Now what is x and y on the curve C1? They are here. They're here, okay? So you put them inside. So x is t, plus 2. And what is y? Y is 1 over 2t. Okay? What is dx? Now you use this one. Right? Right? It's x. Now use this. We are using the formula, but a nice way to remember the formula is this. Is this as we used to do with the change of variable? Is this? It's not like a formal thing, but it's a good thing to remember the formula. This gives you dx is 1 dt, right? Or you just can remember the formula, which tells you that you multiply by x prime of t, which is 1, plus, and then it's dt. Now I am on C1, and C1 is t between 0 and 2. So I'll go from 0 to 2. Plus, I do the exact same thing. Oh, no, we're not over. Because we have to do also for x squared plus, what is x on the first curve? It's t squared. And what is dy? Or you just use the formula. Y prime is 1 over 2. Or is it minus 1 over 2? 1 over 2. 1 over 2. dt. Right? But we're not over, because this is only for plus the second half of the curve, which is C2, and we do the exact same thing. What is C? It's parameterized by x equal to t and 3 minus t. So x is equal to t plus 2, 3 minus t. Okay. Now what is x prime on this curve? It's 1 dt plus, now x is t squared. Now what is y prime on this curve? Is minus 1 and dt. Yeah, so that's how we compute. And now the curve C2 is parameterized by t with the range that goes from 2 to 3. Now once you have done it, so that's it. It's only a matter of calculus. Now you compute, right? You just multiply, which is 2t plus 1 over 2 t squared dt plus integral from 2 to 3 t, sorry, it's 6 minus t minus t squared dt. Okay, We now compute C3. Okay, with C3, okay, here we have a parametric equation of C3, which is x of t is equal to t and y is equal to 0. So x prime of t is 1 and y prime of t is 0. Hence, integral okay, and here, sorry, this t goes from 0 to 3. So y is 0 and x is t, so it's t plus 2 times 0 and 1 dt from 0 to 3. Okay, which is not equal to 5 over 2. Okay, so when you use another curve, even though it's the same starting point and ending point, it's not the same value. It depends on the curve you take. And that's actually very important in physics. You will see why. Okay. Okay, so let me do, so here one thing to remember is, yeah, okay. Now we'll do line integrals of vector fields or work. This is the exact same thing. Okay. Okay, so this is the last section we'll have to do before we go into before we go back to our schedule. Okay, I guess I will take a break right now, and we'll be back at 11:17. Oh, okay. You should have told me that. You should have told me that in the beginning. I was speaking for a while. Okay, that's why I tried, yeah. That's why I ask you every time in the beginning if I have the voice. Now is it fine? Okay. Okay, so let me just go over it that quickly. So if I have a force and I have something that moves from P to Q, and the formula that you know from high school is what is the work done from P to Q by this force. The formula is this. You compute the scalar product, which is just the norm of F times the norm of this vector times cos of theta. And if you're pulling on the object, it's negative. You're pushing on the object, it's positive, right? Now, this is quite cool, but what happens now if it's a bit more complicated than that? What happens if it's a curve, and by curve I mean something that is not a line. And a line is a curve, but it's a basic line. It's a basic curve. So what happens if the path is a curve? But not only that, if the force also is variable, which means that I have a vector field. I mean, something that, for example, a typical example is the sun and the earth, right? Sun and earth, and it's moving around the sun. The force is here, right? The force is radial, goes along the radius or along the line sun earth, and also the curve is an ellipse. It's not right. So that's a typical example. So what's the work? That's a bit more complicated than a line and a scalar product, right? So the force is variable, but also the line is variable. But the thing is this. The thing is, locally, it looks like this. Locally, it looks like this. So that's exactly what we'll do. We're gonna divide the curve, and because it's continuous, it's not gonna vary too much when you're gonna divide it into very small sub curves. So the same formula will apply in a local way. But once you go to a global way, that is calculus actually. Once you go from local to global, you will have an integral. Once you go locally, you have a derivative. Once you go globally, you have an integral. And that happens everywhere. Volumes, line integrals, areas, okay? So locally, it's something simple, right? It's a lot. Locally, it's this. Locally, it's a scalar product and a line. But globally, it's an integral. Okay, to be honest with you, I don't know how much it's gonna take me if I go through all the details. Uh, we might not be able to go through to what we want to do. It's almost 11:25. So let me do a little bit faster than, okay. So the idea here is to divide f into very small, okay, and we have points. Okay, we'll divide them. We'll divide the curve into small curves. Okay, so we'll now take this and zoom. So this looks like a curve. We have the point pi minus 1. We have the point pi. We have the force F, which is F evaluated at some point xi star, yi star, which belongs to the curve. We have the second, the vector pi minus 1 pi, right? And we have the tangent vector here. Okay, evaluated at the point xi star, yi star. Okay, so the work done from pi minus 1 to pi is approximately given by okay, is approximately given by f times x star y star scalar with this vector pi. But here's the thing, this vector pi minus 1 pi, it has a length. Let's call this delta s. Delta s is the length of, is, right? Remember, delta s is the length of the curve from pi minus 1 to pi, which will be approximately given by the length of this segment pi minus 1 pi. So we would like, so what is this pi minus 1 pi? It's approximately given by the tangent unit, the tangent vector, because we would like to have uh, a direction, right, for this pi minus 1 pi. And the best direction you can take here is the tangent vector. It really looks, it looks like the same. It doesn't vary that much from pi minus 1 to pi. It doesn't, you know, if it's a line and if you stay really close to a point, the direction doesn't move that much. So here, it's the same thing, because it's not gonna be that far from the actual direction. So the direction is given by the tangent vector xi star y star times delta s I, where t star it's a unit one. We just wanted the direction. Uh, okay. So as we divide, as we take the limit, well, I mean, so the total work is we divided this curve into these very small lines, right? It's the same exact thing. You have a curve and we divide it into lines, right? So we are approximating the work on these lines, supposing that it's constant on this line, using the formula we know. So when you add up all of these works, scalar with t delta s. So as we take n goes to infinity, we get the sum, we get the line integral of the vector field. And we call it the line integral f times t ds on the curve C. Okay, so now we need a formula for this. So remember, now an actual formula is, so an explicit formula to compute an explicit formula to compute this is given by is. Okay, so what is, I mean, if I give you a curve, let me do this. So okay, what is an explicit formula? Okay, so given a curve RT given by XT, YT. So here, be careful. Sometimes I am using the convention that this is XT, YT, and sometimes I'm using IJ. Okay, so what is the tangent vector? But be careful, because when you compute R prime, it doesn't give you, it gives you the tangent vector, but it doesn't necessarily have unit 1. So a unit tangent vector is given by, because if you have a curve and you compute it will give you something that is tangent to the curve, but not necessarily of unit 1. So you have to renormalize the R prime. So T evaluated at T is R prime divided by the norm of R prime. So that's why we were saying in the beginning that we don't want this to vanish. So, okay. So the work, that's the work, okay? Yeah, I didn't say it, but the line integral, this is also called the work. Done by the force. So the work is given by this line integral okay? Now, here's the thing. I take the vector field because you need to understand the meaning of this line integral. It's the vector field F at a point RT of the curve. It's defined everywhere, but we are moving along the curve. So we have to evaluate this function on the point RT. You need to do the scalar product with this tangent vector T at the point T, which will give you eventually a point xt, yt. So what is this? This is just r prime t divided by r prime t, okay? And what is ds? Remember what is ds? ds is the square root of x prime t plus y prime t squared dt. Okay, so this is ds, and this is also, but r prime t, the norm of this vector, I should actually, I'm sorry here. Just, I would like you to put vectors here. Very important because these are not scalar functions. So the norm of this vector here is this, right? So this is equal to the integral of f evaluated at the point rt times r prime divided by r prime. Okay, here it's very important to know what you're doing. It's the scalar product of two vectors times, it's a number times a number which is the norm of the vector r prime t times a number dt. And now I go over the curve AB. Okay, so suppose I have a curve AB, right? With t between A and B. Okay, so this is like A and B in the timeline. Okay, so be careful. This is a scalar product and this is a number. But now this is a number. So I can actually remove this with this. Because of the properties of scalar product. If you have a scalar number, you can just take it out of the scalar product and then it cancel out with r prime of t, which is a number too. So you're left with the integral from AB of f r of t scalar with r prime of t, the whole thing integrated from A to B, okay? And this will be denoted by the integral of f scalar with dr, okay? So when someone tells you evaluate this, okay? What it means actually, don't be scared or what is this thing? You just have to go back to the definition I gave you here. It's f r of t scalar with r prime dt, you integrate from AB, wherever the curve is. Well, let's do an example, it's much better. Okay, so this is called the work. Okay, so these are all the same ways of saying the exact same thing. It's either, well, these you're gonna never see this. I don't think you will see. I mean, at least in the quiz you'll have this week, or the problem set, will never use this thing here. I mean, unless you're gonna do an exercise for your choice, or someone or another instructor will just show an example or an exercise in the problem set. But I don't think so. No one uses this. So these are the exact same thing of if you see this or you see this, then it means that you have to do this. Okay, so let's do an example. Okay, unfortunately, because of the time, but I really ask you to go and read my notes because this is not an example of the book. So it's an extra example. Um, you can read the example from the book, but this one is not in the book. So I will do only some of these lines. I cannot do all of them. Uh, okay, I will just do maybe C3. Yeah, so let me do an example. Okay, consider the vector field F equal to Y I plus 2xj. Okay, compute the work done by F from 0, 0 to the point P along, well, in the example, if you go to my notes, I gave you 3 paths, and you will have to do it for each path. But as an example here, I'm just gonna do C1, okay? And what is C1? C1 is the line that goes from 0 to 1, and then we go up to the point P. Okay, so the other line from which I'm not gonna do are this line and the circle here, right? And you will see that, right? It's this curve here and this line here, and we're gonna do this curve and this curve. And because it's also piecewise smooth, we can just do it on C1. Okay, C1 will break into 2 pieces. Okay. Okay, so a parameter. Okay, well, so what is the parameterization of C1? From, okay, let's call this one O and this one Q, which is 1, and this one 1. From O to Q. Okay, now this is an example from a physics book from my first year undergrad. R1 T. So yeah, when you do an undergrad in physics, you learn this while you do physics. So so how can I parameterize OQ? It's whatever you want to choose. I mean, you can choose whatever you want. There is not only there is many much more parameterization, but the obvious one is just choose a parameter t. It goes from 0 to 1, and t goes from 0 to 1. And then from Q to P, I have another, sorry, do not forget these vectors. It's gonna help you a lot to just not be confused with scalar functions. And okay, so now I is fixed, so it's the vector I plus, now I can use another parameter t, j, and t goes from 0 to 1. Hence, so on OQ, R prime of t is equal to I on QP R prime of t is equal to j, okay? So the integral over C1 of f dr, remember what it means. I have to break it into two curves that are piecewise, okay? So now I need to evaluate f on R1 of t, do the scalar product with R prime 1. Oh, sorry, this is 1 and this is 2 of t, and then dt, and now it's from 0 to 1 plus from 0 to 1 f evaluated on R2 because I'm on another curve right now, scalar product with the vector R2 prime, the whole thing, I didn't do it here, but the whole thing dt, and now I'm on another curve, but it's parameterized from 0 to 1 as well. Now I plug in, which is the integral from 0 to 1. So what is my vector field? My vector field is given by this function here, okay? So I'm gonna just write it down here. The vector field F, as defined everywhere, is y I plus, and this example is meant to confuse you a little bit because I have y on the x and x on the g on the j. So, right, you have to be careful. So, okay, so I have to evaluate this vector field on the curve R1. The curve R1 is given by Ti. So on the curve R1, I have no y component, okay? So it's 0, I, plus 2, and what is my x? My x is parameterized by t, which is 2t j, okay? And I have to do the scalar product with R1 prime, which is I, and then dt, plus the exact same thing from 0 to 1. Now my vector field is here, and now I am on the curve R2. So what is my y? My y is given by t. So it's t I plus 2, what is x on R2? X on R2 is fixed, is 1. So it's 1, okay? And now j. Now I have to do the scalar product with R2 prime, which is j, okay? dt, okay? Now I do this. Now, scalar product is like normal product, so you multiply this by this and then this by this. But j, I'm just gonna remind you of this, j is perpendicular to I, right? So the scalar product of these two is always 0. So, and the scalar product of I is always 1, and JJ is always 1, right? And J is 0, and JI is 0. So it's the integral from 0 to 1, 0, because 0 times 1, not because they are perpendicular, plus 2t 0, right? Plus the integral from 0 to 1. Now it's t 0 plus 2, 1 dt. Is this too fast? If you have any question, please don't hesitate. Okay, so I'm just gonna recall what I'm doing. This is 0 because we have 0 here. And this is 0 because j and I are perpendicular. And this is 0 because I and j are perpendicular. And j and here's 0 and here's 0 because I and j are perpendicular. And and here's 1 because it's j times j. So it's the integral of 0 to 1 of 2 dt, which is 2, 1, which is 2. So that's how you do it. Okay, so now I'm gonna encourage you to go and read. It's the exact same thing. Parameterize, compute R prime, compute R. Be careful when you see the vector field, plug in and compute one-dimensional integrals. And the purpose of this exercise is to tell you that when you compute this line integral of vector fields, right? This line integrals f times dr, that's the work. It depends on the path you'll take. See, for example, here you're gonna find, let me just give you the answer for the curve C3, which is a circle. Okay, so for example, if you compute this on the circle, C notes, C notes for details, but the integral, so remember, this one was the integral over C1 of f dr. Now, if you look at the notes, it's C2 on C3 to the circle, f dr. How much is it gonna give? CR. It will give you t. It will give you 2 minus pi over 4. 2 minus pi over 4, right? Which is not equal to 2. Okay. So it depends on the path, right? So if you have a curve P and Q, and you take another curve, right? And you have a vector field, and you have this very small tangent vector that you call the R. By the way, it makes sense, these notations of dr over the C, it makes sense because what you're doing actually, you're just taking these very small lines and you're making the scalar product of this line dr with f, and you're doing it over and over again, all over the curve. So this in general will depend on with the path that you'll take. It's not going to give you the same number, depending on the curve you'll take from P to Q, right? So, but in some cases, it'll give you the same number, whatever you choose as a path from P to Q, right? And so we're gonna see this in this next section. So next section is called fundamental theorem for line integrals. Okay, so we take a break at 12:07, but let me just start right now. So remember, the fundamental theorem of calculus. Okay, so remember what it tells you. It tells you that if you want to compute the integral from a to b of a function f prime x dx, it's actually, it depends on f and I. There isn't that much you can say about it because there is only one line from A to B in one dimensional case. So it doesn't really mean anything in the sense that, yeah, because you cannot vary the path from A to B in one dimension unless you're really gonna introduce some holes which will really affect the integral. You can vary it. I mean, you can just remove one point, right? You just can A to a point and then go from there to another point, but without really taking care of this X. But it's only one line, so it's not gonna affect the surface. But so there isn't that much you can see in one dimensional piece. But we just wanted to introduce you to just remember that it's given by this formula here. So the thing is, in two dimensions, there is a similar theorem. Okay, so here is it. So given a function of two variables, okay, call it f x y, and take, so if you take a function of two variables, remember, there is a nice way to create a vector field from this function here and take the gradient delta f x y. Okay, the gradient field. Okay, okay, okay. So that's a vector field, right? So I'm just introducing other notations so that you are aware of it. Okay, take a smooth curve C parameterized by RT, XT, and YT. Okay, for some T between A and B. Okay, suppose that the gradient is continuous. is differentiable. Okay? So let us compute this thing here. Okay, so remember, this is our vector field now. Okay? It's just a very specific vector field. It's something that has to do, it's a vector field that comes from a scalar function. So remember, what is the formula? The formula is you take the gradient of the function, okay? Okay? Evaluated at the point xt, yt, and this, oh, then you take the scalar product with r prime, which is x prime I plus y prime t dt, right? It's going to take it from A to B of f x xt yt times x prime t plus fy xt yt times y prime t, this dt, okay? And this is actually equal to from the integral from A to B. And now remember, first half of the class, you had the change of variable, you have the derivation in chain, which is a function of a function of a two variable function, okay? So it's directly the derivative with respect to t of the function f x t y t, right? Remember this formula? When you have a function of two variables and x and y are themselves functions of a one variable, okay? Now this is a function of one variable, ft. Right? So this is actually the integral from A to B of f prime t dt, which is fb minus f of A. So what is f of b? It's the function f evaluated at the point B minus the function f x evaluated at the point A okay, which is the function f. This is what we're going to see in the book, evaluated at the point RB minus f evaluated at the point RA. So the integral of a gradient of a function times dr on a curve is actually equal to f r of b minus f of r of a. Okay. So what does it tell you? What does it tell you is if you have a curve C, right? And the point RA and the point RB, okay? And then you take another curve, okay? What it tells you is the line integral okay, formula star star, or let me say formula 1 says that the integral over C1 is actually the same thing as equal. So the work does not depend on the curve from, let's call this one P and this one Q. P, okay? So that's actually not exactly, that's very different from the example. The example, what it depended on the curve that we took, remember? But once you have this very specific kind of vector fields, uh, it does not depend. It does not depend on. It does not depend on the path you take from P to Q, right? So now this will introduce us to the concept of independence of path. Okay, independence of path. Right? So we will now define something much more general than this formula. It happens sometimes when the function arises, when the vector field arises from a function of two variables, but it's much more general. We're just going to introduce now the concept of path independence, which will just tell you, I mean, basically what it means is a vector field, whatever, I mean, wherever it comes from, we'll just say that it does not depend on the path if Whatever the curve you take, it gives you the same number. That's the definition. So from this definition, we will now call these gradient fields time independent, because we've just proved that they do not depend on the path. It's kind of very specific um, time independent vector fields. And you will see that actually they are the only, in some cases, they are the only time independent path. So let me take a break and let me be back at 12:23. Welcome back, everyone. I cannot listen. No, it was on mute. So don't worry. It was on mute. Okay. So independence of path. Okay. But now you can hear the voice, right? Okay. Given a vector field, uh, we say that this integral is path independent. I feel like the name path independent is much more, at least this is the name I've seen somewhere else. But the book uses a longer one. It's independent of the path or something. If the integral C, the integral over C1 is equal to integral over C2 for any two paths, C1 and C2, with the same endpoints. right? And by this, I mean, I have the same endpoint, and I am having two curves, C1 and C2. So remember, what is a conservative vector field? So conservative, so this is why actually they're called conservative. Conservative vector field. But you guys remember what is a conservative vector field mean, right? Okay. Fields of the form gradient of fx for some function fxy. So here's some other terminology. A curve is closed if the initial point is equal to the terminal point. Okay, so for example, if you have a curve and then same point, you start from P and you go back to P, right? And then you go, this is a curve. Okay, so now we will, okay, 12:30. Okay. So for the rest of today, I don't think we're gonna go further than this. We will now investigate the question of, okay, when is it that a vector field is time dependent, is path independent or not? So the first step actually will be to give an equivalent definition of what we mean by path independent. So this is okay. The result is this. If I have a vector field, okay, this is path independent. This is the same thing as saying that the integral is 0 for every closed curve. Okay? But this is not really hard to see. I mean, what is the proof? Okay, so make sure you understand this. Okay? Yeah. Why? Okay, so here's the reason. I mean, take a curve. Here you have to go into two directions, right? take a curve and start from A and then go to B. Okay? So let's go in one direction, right? Suppose that it's path independent, right? And take a closed curve. Okay? So we'll go from this direction, we'll go over here, AB, and then, okay? And then we'll go, this is the curve C. Okay, so the integral from, so we'll call this one C1, and then from B, okay? So we call this B. So because this is path independent, the integral on C1 of f dr is equal to the integral on C2 f dr. It doesn't matter, it's the same endpoints, A and B. Okay? Now, here's one thing to remember. If you go backward, which means I'll go in this direction instead, right? This is the curve minus C2. So the thing what happens is if you go minus C2, right? The thing is this, if we go backward, you will still have the same quantities. It's the same F everywhere. It's just instead of going in this direction, dr, the dr will be on the other direction, right? So when you are computing this scalar product, right? This is theta, right? This is, for example, let me do it. So if you have the curve and you have F and you have dr and you have theta, when you go, this is this direction. Now when you go on the other direction, it's the same tangent, it's a tangent line. So it's just on the other direction, you have dr. But then you will have minus, it's a 180 minus, right? This angle here is 180 minus theta. Oh, we are in a math class right now. So pi minus theta. So cos of pi minus theta is minus cos theta, right? So what happens actually is you're gonna pick a factor of minus all along the line. So, but you still have the same vectors, you still have the same norms, so you have minus here. So that's the reason. Okay. Oh, sorry about that. Sorry. Okay, sorry. Because it's very time independent, we'll have this. Because going from A to B, you will have to take a path from A to B. And C2 is not from A to B, it's from B to A. Because the path is you have to give an orientation for the path. And C2 as here, it's from B to A, so you have to give minus C2. So because it's time independent, it doesn't depend on the path. It gives the same number if you take C1 or C2. And now, because of what I just said, let me just check this. Because of what I just said, this is gonna be minus of C1 of C2. Okay? So the integral of C1 dr plus the integral of C2 dr is equal to 0, right? Now, this is the integral on C1 union C2. Remember, we can break down these curves into piecewise curves. So it's the same thing. Which is the integral over C dr, right? Because C1 followed by C2 is actually the whole C, which is, we started with C. So this gives one direction. And I will leave it to you as an exercise to check the other direction. It's the same thing actually. If you have a closed curve that is equal to 0, then it does not depend on the path. It's exactly the same thing. I mean, you start, but now what you want to show, this is an exercise. I mean, what you want to show is you take A, B, and you take two paths, one that goes from here, and then the other one you take from here, right? And then you just have to make sure that you have the right orientations, and you will have to use at some point that here you'll have to take AB followed by minus. You'll have to take C1, C2, and you want to show that they give you the same line integral. Now you have to consider minus C2 and use the fact that when you go C1 and minus C2, it's 0, because you're supposing that this is true and you want to prove this. So it's the same, really the same argument, but just on the other way. So this is another formulation of the definition of path independent. I mean, whenever you have a closed curve and it gives you 0 when you do the line integral, it's supposed to give you 0 when it's path independent. So now the question is, okay, I give you a vector field and I ask you, is it time independent? Well, we have done some work, right? We have moved from the situation where you'll have to test it on every possible curve from A to B, and now you just have to check it on closed curves. Okay, it's not that much, but it's still a lot of work, because you have to consider every kind of closed curve you can imagine and compute it on this closed curve and check that it's 0. And do it for all kind of closed curves you can imagine, which is an infinite number of them. But so obviously this is not something that mathematicians like. You cannot check this. You cannot check this like in real life. You cannot check it, at least in this formulation. So you have to do a bit more work to check if a vector field does or not depend on the path. So now we'll, okay. Now, so obviously, good things are true in math only when there are a lot of hypotheses you have to check. So, so first one is you have to take. So that's why I'm going to introduce this very technical term. So consider an open. So here it will be a very technical part. Consider an open connected region D. in the XY plane. Okay? Okay, I'm gonna remind you what is connected and what is open. So if you have a region D, opens mean whatever a point X and Y you choose. You can find a small wall, a small circle that goes inside the domain. This is open. And connected means if I give you another point, X prime, Y prime, inside D, I can find a path that goes from D and the path stays in D. This is what it means to be connected. I mean, whatever 2 points, you can find a path. I mean, for example, if I have this with a hole here, right? And the region here, this is connected. It's not simply connected, but it's connected. And we'll see how infer down the line what it means to be simply connected. But it's connected, which means that if I give you 2 points, you can see that, I mean, intuitively. If you give you 2 points, you can find all right, even though it's like here, you can find a curve, you can find a curve that's gonna avoid and contour this hole. Connected. Okay? Okay. And for this kind of open connected regions, okay? So theorem, okay, let F be a continuous vector field on an open connected region V. Okay? If this integral is path independent, then F is a conservative vector field, which on V, which means that F looks like the gradient of a function for some function F. Okay? That's pretty much good because actually for this kind of open connected regions, the only time independent line integrals vector fields are those that are from scalar functions. These are the only ones. Okay. Okay, I can prove this, but I will either let you read the proof because it's in my notes and it's very well explained, or so. But I would like to move, but I would like to show you something else. Uh, but it's very important that you understand what is a theorem saying and how to know how to apply it. Now the thing is, this theorem is not going to be really practical. It's not going to be that practical in real life. It's like you have to be open and connected. Yes, a lot of these regions, but because we would like to have a very, very specific way to see if it's a path independent. I mean, the question is, I give you a vector field and I ask you, is it path independent? That's really the most important thing we would like to see. We'd like to check. Now, if it's path independent, if your answer is yes, and if the region is open and connected, then yeah, it comes from a gradient. Okay, that's good. But now but what I want to know is really is like, is it path independent without having to check it on every possible closed curve? So here comes the very important theorem that says yes, but we have to be a much more restrictive than connected regions. So proof, I think I will leave it as an exercise or notes, right? Or if times allows. But let me move to simply connected regions. Now, let me see. Yeah. So first of all, let us see something. Let us observe the following thing. Okay, back to our question. Our question is this path independent? Okay. Okay. Or okay. Suppose that F is known to be conservative. Okay, but here, make sure that you understand what we are saying. Conservative means that it's path independent, okay? But path independent doesn't necessarily mean that it's conservative, right? Path independent is only true that it's conservative if the region is open and it's connected by the theorem. So now we're gonna try to answer a little bit less dramatic question, which is not only is it time independent, but is it conservative, right? Because if you can say that it's conservative, then yes, it's path independent. Okay, so suppose it's conservative. So f is the gradient of some function f. Okay? And suppose that f is given by pxy I plus qxy j. With p and q with have continuous first order derivatives. Okay? So what it means, f is actually derivative of dxp I plus dy q j. Okay? Oh, sorry. Okay? But because it's conservative, it's actually equal to dx fx. Okay? Which means that p is equal to dx fxy and q is equal to dy fxy. So because these functions they have continuous first order derivatives, so Darboux, what was called the you've seen this in the first half rule. It's called the Darboux rule or something rule. It means that d but since dy, remember this, if you have a continuous functions with continuous first derivatives, this is equal to, you can switch the order. This is kind of Fubini's theorem, but for the derivatives, right? Well, do it here, right? Since this we get, so if we apply dy to the first one and dx to the second one, we get that dy of p, it's dy dx. And then we apply it to the second one, which is dx dy fxy. But these are equal if it's continuous. We are supposing that everything is fine here, but these are equal, which means that dy is equal to dx. Okay? But here is a very important thing to remember. You must be tempted to say, okay, that must be true. Whenever I have a conservative vector field, it's one direction only. If it's conservative, if it's conservative, then I have this. Okay, then I have this. Right? If it's conservative, F is conservative, if F is conservative, then I have this. Now you might be tempted to say, okay, give me a vector field. I'm just gonna check this. And if it's true, then it's conservative. No, but you didn't prove it. You just proved that if it's conservative, then this might be true. This is true for sure. If the function is continuous, and we will, in real life we're gonna deal with this kind of cute functions. But But the thing is, if you want to go on the other direction, it's not really that easy. If you want to, if you want to check that if this is true, then it must be conservative. That is still a lot of work to prove it. And it turns out that it's true, only for some cases. Okay? Okay. Terminology here, some terminology, simply connected. Readers. Intuitively speaking, these regions, they have no holes. I mean, if you have a region with a hole, this is not simply connected. Not simply connected. Now, there's a very technical definition of simply connected, but I don't want to give you this here. It has to do with loops and fundamental domain and all of that, and fundamental group and all of that, which means like homotopy things and loops, and you have to deform continuously the loops. But we'll just stick with this is not. But you are only asked to understand this in this level, not simply, but it is connected, not simply connected. So what is the right way to do it? So it's simply connected. The right way to say it is, I think I have it somewhere. Or did we just, we're just gonna be stuck here? All right, so for now, just keep in mind that simply connected means that there is no hole. Okay, and there are a couple of pictures in the book that shows other that shows other this is chapter 15. No, it's chapter 16. And okay. Here. See? So this kind of so this diagram here uh, it tells you a couple of examples. See? But it only gives an intuitive level. Okay? So this is simply connected, and when it's not, this is not even connected. This is not even connected, right? Because you cannot just go from one point to another point, right? So this is not even connected. So it cannot be simply connected. This is connected, but not simply connected because you have a hole and you have two holes here. So it's not simply connected. And this one is connected. Okay? Right? And in terms of simple curves also, we'll need simple curves. The terminology, it's also easy. I mean, simple curve means that the only times the curve will cross itself is at the end points, right? There will be no such a, right? This is simple. So when it's not simple, it has other crossing than the first one you start with, right? So you start with 2, and then, for example, if it's a closed curve, you start with the point, and if it crosses again itself, then it's not included. Okay. The only time it's going to cross itself is the first one. So that's for the terminology, and I don't want to go through the details, but that's the terminology we're going to use. So okay, it's almost 1 o'clock. I'm going to let you go, but we'll finish the next time. Okay. Have a nice day, everyone. See you tomorrow. Any questions, by the way? Okay, I'm going to stop the recording right now.